Since the derivative of e to the x is e to the x, the integral of e to the x is e to the x plus a constant. So we could write this. Now, the integral of e to the u du is e to the u plus a constant. The trick in dealing with this situation, we'll go right to the situation of the u, where u is an expression involving x. But the trick in dealing with this is to take care of the du part. For example, the integral of e to the 3x plus 1 dx. Well, we think of this as the u, and we might come out to the side and actively think and write down u is 3x plus 1, so du is 3 dx. Now, 3 dx is what we want to appear right here, you see, to have the du form. So let's see, we need a 3-factor. We can accomplish a 3-factor by multiplying by 1/3 out here and 3 inside. So 1/3 out here, 3 inside. This is the form we need. So it's e to the u du, you see, and therefore the integral is e to the u, or e to the 3x plus 1, and it's multiplied times 1/3, and we add a constant. Now, there are a couple of different ways of handling this substitution. Here we just pretty much did it mentally. Let's take a look at another problem. We have the integral of 5x e to the negative x squared dx. And as soon as we see a constant involved, I suggest we just snag it out and write it outside of the integration. Okay. Now we're thinking in terms of, we've got e to the negative x squared. We have an x factor here. We have dx. Well, we know this is going to be the u part. So we might come out to the side and say u is negative x squared. Du then is, well, the derivative of this, negative 2x dx. All right, so we need to have all of this, and what do we have? Well, we have dx, we have x, so we have x dx. Now, to emphasize what we have, we might rewrite as the x dx next to one another like this, and even emphasize that's what we have. And what we need is negative 2x dx. Okay, we can accomplish the negative 2. Pop the negative 2 in here if we have a negative 1/2 out here. And that's the way we proceed. Now we have the form that we want, e to the u du, and so we have the integral of e to the negative x squared is negative e to the negative x squared. So we have this, and then we tack on the constant. Now there's another way to proceed here, and some people prefer to make an active substitution. And let me go through the process with the same problem and just step through the logic pattern for that. We start in much the same way. We have 5x e to the negative x squared dx. All right, we snag out the 5 right quick. We probably would be wise to resort the other factors so that we have e to the u, you see, separate from the other factors. So, and I've done that here. All right, now it's at this point in the problem that we would come out to the side and say, all right, u is the negative x squared, the du is negative 2x dx. Now, what we have in our problem is the x dx. So what I could do over here for substitution purposes is I could solve this for x dx. And to solve that for x dx, this is du over negative 2 equals x dx. All right, now I can rewrite over here, replacing x dx with this fraction. Let's go over here and do that. So the x dx is the du over negative 2. And this, since the u is negative x squared, we have the u here. All right, now we want to accomplish the form over here to the right of the integration symbol is the e to the u du. So we need to snag out the negative 2. And since it's in a denominator, it manifests itself as 5 over negative 2 outside. Now we have e to the u du, so the integral is e to the u. And then we tack on the constant c. Then we back substitute. The u is negative x squared. So some people feel like this is a little bit cleaner, a little bit easier to see through if we make these active substitutions, but sometimes it adds a step or so to the problem. Here's another one. The integral of e to the 1 over x all over x squared dx. Now, let's go through that separation process right quick. That is, we want the e to the u part. We want to write that first, and then we want to write sort of everything else after that. So it's e to the 1 over x, and then move this x squared in the denominator over by writing it as 1 over x squared dx. Now we identify the u part as 1 over x, which is x to the negative 1. So du then is negative 1x to the negative 2 dx, but this is negative 1 over x squared dx. Now we could go through that substitution process, but we can understand that we want to be looking at this for the du part, and what we have is this, and they're very similar. All we need is a negative sign in here. So we'll just pop in a negative out here, a negative in here, and away we go. We have what we need, so it's e to the u, you see, or e to the 1 over x is the integral here, and we have our negative sign and we have a constant. In this section, we're going to be integrating the natural log function, and it probably makes sense that we're going to use as the basis the differentiation, because it's kind of the opposite idea. In the last section, we talked about the derivative of ln x is 1 over x, and it's understood here that x is greater than 0. Now that's kind of implied by the nature of ln x. If ln x makes any sense, since we can only take the natural log of positive numbers, if this makes sense, then x has to be positive. So at any rate, this sort of disclaimer is in here, and I'm pointing it out because of what's going to happen a little bit later. Anyway, we take this situation and we're going to kind of work it in reverse in order to integrate. So I'm just writing these on opposite sides, so we have 1 over x equals the derivative of ln x. Now let's integrate on both sides. So the integral of 1 over x dx, now undo derivative, so we get ln x plus a constant. Now notice the absolute value here. It's kind of necessary in this situation, because if we're starting with 1 over x and we're going to integrate the 1 over x, then we would like to be able to integrate this situation whether x is positive or negative. And in order to guarantee us that the ln x part is going to make sense, we just apply that absolute value idea. Now, from a conceptual standpoint, we know that we have to go about matters like this because the general power rule simply doesn't work in this circumstance. You know, we can rewrite this as x to the negative 1. And if we're thinking about the general power rule, remember there was a disclaimer in the general power rule. It said that we'll use that power rule as long as the exponent is not negative 1. You see, so it applies in all cases except this one. And the reason it doesn't apply is because if we tried to apply it, we would get, well, let's see, increase this by 1, so we get we get 0, and then in the denominator we get 0. And that 0 in the denominator is the big problem here. Well, at any rate, so we have a way of integrating, and we'd like to generalize the idea. This is a very specific idea of a single variable, but what if we have an expression that's written in terms of x? And it's the idea of, in the last section we were talking about the derivative of ln u, where u is a function of x. And it turns out to be 1 over u du dx, or the derivative of u with respect to x. Now this notation is fine. There's another notation I think that's a little bit cleaner than this. If we understand that du is u prime dx, imagine replacing the du with the u prime dx. The dx notations would go out, and we would have u prime over here and then u prime over u. So I kind of like this kind of notation for it, because it's really easy to see and to manipulate. Well, at any rate, let's swap these around and then take the integral on both sides. So the integral of the u prime u dx is ln u plus c. Now notice it's ln absolute value of u. And another way to, if we backtrack on this kind of notation, this u prime dx, if we backtrack on that, it's du over u. So either way we look at it, it's okay. Let's take a few problems. We're looking to see that pattern of the u prime over u, and here we're taking the integral of 1 over 6x plus 1. Well, is the 1 the derivative of 6x plus 1? Well, no, we need a 6 up here, and we resort to some trickery. We'll multiply by 6 times 1/6, then we'll put the 6 in this numerator and the 1/6 out here. And now we have the u prime over u idea, and it's real easy to see through. So that integral then is natural log of the absolute value of the denominator. And that's really all there is to it. So it's 1/6 natural log of the absolute value of the denominator plus a constant. Here's another one. And again, we're just looking for that u prime over u idea, and we're asking ourselves, is this the derivative of that? Well, let's see. The derivative of 3x would be 2x squared. Excuse me. The derivative of x cubed would be 3x squared, and we have that up here. The derivative of x would be 1. So yes, we do have the condition that we need, and so it's the natural log of the absolute value of the denominator plus a constant. Here's another one. We've got, now, look for the derivative of the denominator. The derivative of the denominator needs to appear in the numerator for us to apply this definition, this idea. So let's see, the derivative of 2x, of x squared would be 2x. Well, we only have an x here, we need a 2 factor. The derivative of 2x would be 2. Gee, we need a 2 here. So we need to multiply in the numerator by 2. We can do that again by multiplying by 1/2 times 2, put the 2 inside, the 1/2 outside, and we have the condition that we need. So this is 1/2 the natural log of the absolute value of the denominator plus a constant. And this applies to trigonometric functions as well. Here we see tangent x in the denominator. The derivative of tangent x is secant squared x, so we have the conditions that we need to take the integral. So this is the natural log then of the absolute value of the denominator plus a constant. Here's one that requires a little more manipulation. Notice that we just have 1 in the numerator and we have these 2 factors in the denominator. I'm going to kick the x to the 2/3 to the numerator and write it as x to the negative 2/3. And now, because of the complication, we might go into the substitution idea, so thinking of this as u and investigating for u prime. So we're going to substitute or think about x to the 1/3 plus 1 as u. Now u prime then, see, we can work with the idea of u prime kind of as a separate from looking at this. Now we may be able to see through it like this and we may not. It really doesn't make a great deal of difference here, I don't think, but I want to show you how this routine works out. So the u prime, let's see, the derivative of x to the 1/3 is 1/3 x to the negative 2/3. Well, that's nice because we have the x to the negative 2/3 already up here. We just need the 1/3 factor, and this kind of reminds us of that. And so we'll pop in the 1/3 factor here and a 3 out here, and then we're ready to go. Now we have the conditions that we're after. It's u prime over u dx, and so it's 3 times the natural log of the absolute value of the denominator plus a constant. Now, about right here in the development of this problem, we could actually physically make the substitution. I didn't actually make the substitution here. I used the substitution in order to figure some things out about the 1/3 and the 3. But I could actually make the substitution here, and the substitution I would make would come from taking this expression and kind of solving it for the numerator. How can I replace here for the numerator? And I would do that by multiplying on both sides by 3. So I would have 3u prime equals x to the negative 2/3. In other words, 3u prime equals x to the negative 2/3. Now, with that, I can substitute back into the expression before, and the x to the negative 2/3 numerator becomes 3u prime. And then the denominator was the u. And now, since I'm looking for the u prime over u situation, I'll just take this numerator factor, this constant, and kick it to the outside. And now I have the conditions that I want, so it's 3 natural log absolute value of denominator plus constant, back substitute for u, and I have the answer that I got before. Now this method is, I think it's a little bit cleaner than the other method, and it's a method that we'll need to use in other problems in the future. But sometimes it's just a little bit longer, a step or two longer. We're going to look now at a couple of nuances in this process, and these nuances are taken care of by particular manipulations. Let me show you what I mean. Here we have a situation where we're taking the integral, and we notice that the degree of the polynomial numerator is the same as the degree of the polynomial denominator. Now, in this circumstance, we can't possibly achieve or see right away that we have a u prime over u condition. So we'll to manipulate it, to change it into some other form that might meet our requirements, one thing we could do is perform long division. That is, anytime the degree of the numerator is the same as or higher than the degree of the denominator, we can resort to this kind of manipulation. So I'm dividing x squared plus 1 into the numerator polynomial, and you remember this process, x squared into x squared goes one time. We put the 1 up here. Usually we try to line up terms of the same degree. So I would put the 1 over here, 1 times x squared, and then 1 times 1, 1. Draw the line and subtract, and we had ways of doing this, but when we subtract these, they go out. We bring down the x, and so x is the remainder because it is of a degree lower than the x squared. Okay, so the complete answer in this situation is 1 plus the remainder over the divisor. So it's really 1 plus x over x squared plus 1. Now we can rewrite this then in this form. So it is the integral then of 1 plus x over x squared plus 1. And now we can sort of separate our problem into sort of two integration problems. Let's take it from up here. Here's the same step that we had below. So it's the integral of 1 dx, or just dx. The 1 is in here just for emphasis, but plus the integral of this fraction dx. And now we can apply this idea of the u prime over u, and this we can handle from our previous experience. Well, here we're looking for the u prime over u situation, and the derivative of x squared is 2x, so we need a 2. So we apply an outside 1/2 factor and then an inside factor of 2, and we have the conditions that we need. So this part becomes 1/2 natural log. It would be absolute value of x squared plus 1 plus the constant, but we don't really need absolute value here because it's guaranteed that this value will be positive because of the x squared. Okay, at any rate, and here the integral of 1 dx is simply x. So that's one situation that we can apply in this matter of integration. And you know, when you first bump into a problem, when you first look at a problem in integration, you're not sure that whether or not we're going to be using this idea of natural log. If you were looking at a battery of problems and you were taking them at face value, then you would bump into the situations that cause you to apply this idea of natural log. Now, and because of that, use the manipulative processes that we have encountered before and just see what you bump into. When you bump into the circumstance of the u prime over u, or the 1 over x, then that's when you're applying this idea of natural log. Here's a problem that involves another nuance. It's 2x over x plus 1 all squared, and we're taking the integral. Now, I'm using as u the x plus 1. Now we're not, let's say that we're not expecting to run into the natural log idea, the idea of the integration of the 1 over x or the u prime over u. But we may run into it. And that's the way we need to view the situation. It's not the case that even though we're in a section that deals with this, it's not the case that every problem will have that situation occur. So let's just go through and follow our nose through here and perform a substitution. U is x plus 1. Well, du is 1 dx. Now I'm using a du notation here because I'm going to completely go into the substitution form here, and I'd like to use du rather than have a dx sticking in there. But gee, with the du is 1 dx, these are pretty much interchangeable, aren't they? But at any rate, we need a substitution in this numerator. You see, we don't have a sort of a natural substitution in the numerator here, so we need to solve this for x, because we'll need to replace the x with something in terms of u, and that's kind of built in here. Solve this for x, we have x is u minus 1. So now we can write the expression as 2 times u minus 1 with this substitution, and then since u is the x plus 1 in the denominator, it's u squared in the denominator, and I can write this as du. So a rather clean kind of notation here. Now the 2 we can just yank out of the whole process and consider this. We can make this into two fractions, u over u squared minus 1 over u squared, kind of like this. And now we can reduce here and rewrite here. So let's do that up here. We have remember that 2 was outside of the integration symbol, so we have 2 times the integral of 1 over u du, and then minus 2 times the integral of u to the negative 2 power. And we just look around to see, oh, well, here we are using that idea that we talk about, the natural log idea. So it's 2 natural log absolute value of u, and then over here minus 2 u to the negative 1 over negative 1, and we can clean this up a little bit. The negative becomes positive, and this is 2 times 1 over u, and then we just do a back substitution. U is x plus 1 in both cases, and we're done.